Okay, so in this video we're going to talk about something called the binomial distribution, and I'm going to introduce that with a little problem here. So suppose we roll 3 dice, and we want to know what the probability is of getting exactly 1 5. So let's think about this for a second. We have the idea of a success, which is rolling a 5, and we want exactly one of them. So let's define that. Let's call our success, we'll use the letter S for success. This is going to be rolling a 5. And let's call F failure, I guess, is not rolling a 5. And, well, we know how dice work. We know the probability of rolling a 5 on just one die. And let's be clear here, both of these are on one die. We know the probability of rolling a 5 on one die is a sixth. There's 1 5 and 6 different faces on a die. And the probability of not rolling a 5, well, it's the rest of it. 1 minus a sixth, which is 5 sixths. So let's use these two facts here to help us out. So we can think of it, there's 3 dice that we have. So let's call them die 1, die 2, and die 3. And we can make a little table here. So one way that we can satisfy rolling 3 dice and having exactly 1 5 is maybe the first die is our 5 and the other 2 aren't. Or maybe our second die is a 5 and the other 2 aren't. And finally, maybe the last die is a 5 and the other 2 aren't. And we can calculate the probability in each of these cases. Remember, we're rolling 3 dice. Each die roll is independent of the other die rolls. Rolling a 5 on one dice doesn't change the probability of rolling a 5 on any other die. And the probability of rolling a 5 is the same across all dice. We're picking 3 dice that have the same probabilities per dice. So there's a fixed probability of success in each of these 3 cases, and that's going to be important to us. But we know that these are independent and the probabilities are fixed for each die, so that's great. So in the first case, well, we can just calculate the probabilities here by multiplying the probabilities, since we want a success on die 1 and a failure on die 2 and a failure on die 3. These are nice and independent of each other. So the probability of success, we said, was a sixth, and the probability of failure is 5 sixths. There we go. Which I'm going to write as 1 6th times 5 sixths squared, since we have 5 6 multiplied by itself twice. Well, let's look at the second case. Well, it's almost the same. We just have a different order of the dice. So 5 6 times 1 6 times 5 sixths. But we all know multiplication is commutative. We can multiply in any order we want. So we can rearrange this to be the exact same thing as the first example. And the last example, I won't even write it out. It's going to be the exact same thing as the other 2. Multiplication is commutative. You can move it around. So the probability is the same. And now, the other thing I want you to note is that getting a 5 on die 1 and not on the other 2 is mutually exclusive to getting a 5 on die 2 and not the other 2, which is mutually exclusive to getting a 5 on die 3 and not the other 2. So to find the probability of getting exactly 1 5, in fact, we can define this as a random variable. Let's let x be the number of 5s rolled out of our 3 dice, then the probability that we get exactly 1, 5, that x equals 1, well, it's going to be the sum of the probabilities in each of these three cases. Since we can get our success on die 1, or we can get a success on die 2, or we can get our success on die 3, and these are mutually exclusive. So I have 3 different cases where we have the same probability. So it's 3 times a sixth times 5/6 squared. And if you put that into your calculator, you should get, well, 75 over 216, or as a decimal, that's roughly 0.3472. So roughly a 35% chance of getting exactly 1, 5 if you roll 3 dice. Now we'll generalize this on the next slide here, but I want to point out the things that kind of don't matter. We didn't really care what this probability of success is here. We would just put if we have a different probability of success, we would have put it in here. Probability of failure is just 1 minus the probability of success, so we'd put it in there. And then what's this 3? Well, if we think about it, this reminds us of an arrangement of symbols problem. We want to count the number of ways we can arrange one S with 2 Fs, one success, with the rest failures. So this here we're thinking of as 3 factorial over 1 factorial, 2 factorial, which we can think of as 3 choose 1, since we want 1 success and the rest failures out of 3 symbols in total. So we're thinking of this 3 here, we're thinking of this as 3 choose 1. That's important for generalizing this to kind of any situation. And one more thing I want to point out. I'm just going to put, for right now, I'm going to put a power of 1 here above the 1/6 here, since we know anything to the 1 is just itself. But the reason I'm doing that is we can think of these powers here telling us how many successes we have. We have 1 success that we want, and how many failures, the rest failures. Here we have 2 failures. So putting all those together, we can generalize it on the next slide. So let's talk about the setup here. There kind of was nothing special about rolling dice. The only thing that we wanted is that we had a bunch of independent trials. In the last example, we rolled 3 dice. All of the dice were independent of each other. Just because I rolled something on one die wouldn't affect the probabilities of rolling any other outcome on the other. So n independent trials, and in the last case, n was 3. We viewed the problem as having 2 outcomes. Success, which for us was rolling a 5, and failure, which was not rolling a 5. So we can group our outcomes into successes and failures. And the other thing, for each trial, the probability of success, and therefore the probability of failure, is fixed. It's the same for each trial. So rolling a die wasn't anything special. Anything that satisfies these characteristics, we can use the following idea for. So if we call our random variable x the number of successes, then if we want to know the probability of getting k successes in this case, well, it's going to be, I'll come back to this term in a second, we want k successes, and each success has a probability of p of attaining it, so it's p to the power k, p multiplied by itself k times the probability of failure multiplied by itself the rest amount of times, n minus k. If we have k successes, we have the rest, n minus k failures. And then we have this n choose k in front of it. Remember, this is telling us how many different ways there are to arrange our successes and failures. Number of ways arranging. What do we want? We want K successes and the rest, N minus K, failures. Any different arrangement of the S's and F's gives us a new possibility of where our successes live, just like in the previous example. So we can use this formula to build up a distribution. If we just let K range all the way from having 0 successes, so no successes, to all successes, so K equals N, that will give us the entire probability distribution for this scenario. And that's called the binomial distribution. Let's look at an example, and then we'll look at a couple of features of it. Let's look at this example. So we're talking a bit of workplace here, and we're going to assume that the probability that an employee is on vacation on a certain day is 5%. And we're going to assume that that's fixed across all employees, and also that all employees are independent of each other. Just because one person is on vacation doesn't affect the probability that somebody else will take that vacation. That might not be super true in real life, but for the purposes of this question, let's just go with it. So let's say our workplace has 8 individuals. The first question is, I want to know what's the probability that exactly 2 are on vacation. And the second is that the workplace can't operate if there are fewer than 6 employees. I want to know what's the probability that it cannot operate. So it's a good idea now to pause the video and think about these questions. Part A should be quite easy. It's just basically the same idea as the first example that we did. B, you're going to have to think about the ideas of probabilities of mutually exclusive events. And to make your life easy, maybe thinking about complementary events will help you as well. So pause the video now, see if you can work these out, and we'll go on and solve them on the next slide. Okay, so for this is just a straight up looking at what's the probability that we have 2 people on vacation. So let's define, before I write down this, in fact, I'm going to erase this, and let's define what X is. X is number of people on vacation. And then, well, let's call a success being on vacation. And let's call a failure not on vacation. And we know the probability of success, we're told, is 5%, 0.05. And the probability of failure is the rest of it, 95%. So 1 minus 0.05 is 0.95. Okay, so we know that. And I just want to point out, you could do this problem by flipping what a success and a failure is. Maybe you want a success being not on vacation and a failure being on vacation, but the math will work out the same. So here, we want the probability that the number of people on vacation is 2. So using our formula, remember it's the number of symbols in total, or the number of people in total, so that in this case is 8. We want to choose 2 of them to be on vacation and the other 6 to not be on vacation. And we want to multiply by the probability of success, 0.05 squared. And then the probability of failure, 1 minus 0.05, so 0.95, to the rest, to the power of 6. So just to include what's going on here, this is the same thing. This is n, choose k. This is the probability of success to the k, and the probability of failure to the rest. Just a reminder of how our formula works. And then it's just typing this into your calculator. And if we do type that into our calculator, we get, let me do this in black, we get roughly 0.0514 to three significant figures. In fact, maybe let's say 515. Let's round up there since I should. So there's a 5.15% chance exactly 2 people will be on vacation, and that's part A. Part B says, well, we want to find the probability that they cannot operate. So we want to find the probability that there are fewer than 6 employees, which means that 3 or more employees are on vacation. So we're looking for the probability that the number of people on vacation is greater than or equal to 3. And I'm going to write this out the long way. I'm not going to do it. But this is the probability that x is 3, or it can be 4 people on vacation, or it can be 5 people, or it can be 6 people, or it can be 7 people, or it can be 8 people. And if we wanted to, we could do that computation, figure out the probability when x is 3, 4, 5, 6, 7, and 8. That's 6 separate formulas just like this. But we can be a little bit clever. And we can realize that this is the same thing as the complement of x being less than or equal to 2. So having 2, 1, or 0 people on vacation, that would mean that we can operate, and the probability that we can't operate is just the complementary event. So it's 1 minus that probability. And this is a little bit easier to figure out. There's only a few things that we need to calculate. If x is less than or equal to 2, then that means that the number of people on vacation is 0, or the number of people on vacation is 1, or the number of people on vacation is 2. And we already worked out this bit, so that's quite easy for us. We just need to figure out the probability when x is 0 and x is 1. And notice that I put brackets around this here. A lot of students kind of forget to do that, and they'll put 1 minus px equals 0 plus px equals 1 plus px equals 2 without the brackets. But then you'll make some sign errors here because we're subtracting this whole thing. So make sure that you put brackets around that and calculate that separately and then subtract it from 1. Okay, so we know this. We can fill that in later. So we just need the probability when x equals 0. So let's go ahead. Probability that x equals 0. That's going to be, well, there's 8 employees. We want 0 of them to be on vacation. And then it's 0.05 to the 0 times 0.95 to the 8. And anything choose 0 is 1. So this is very easy to calculate. That's 1. Anything to the power 0 is 1, except for 0 itself, but don't worry about that. And 0.95 to the 8, that's easy enough to put into our calculator. Let's do that. And we get that the probability that nobody is on vacation on a certain day is 0.6634, we'll say. So there's a 66.34% chance that there is nobody on vacation on this day. And the probability that x equals 1, well, that's going to be 8 choose 1 times 0.05 to the 1, the probability of success to the 1. We want 1 success, 1 person on vacation, and the rest are not, so the rest count as failures, 0.95 to the rest, to the 7. And we just put that into our calculator. 8 choose 1, well, that's pretty easy, that's just 8, and then we need to put these numbers into our calculator. Let's go ahead and do that. And we get to 4 decimal places 0.2793. Great. So we have all of our pieces here. Let's highlight these. So we figured out that probability, we figured out that probability, and we figured out that probability. So if we add those together, let's just go down here. Maybe I will put these to the side. So let's go down here. So this equals 1 minus, if I add those together, we get 0.9942. If we subtract that from 1, we get 0.0058. So the probability, the workplace cannot operate, is, well, as a decimal, not as a decimal, as a percentage, 0.58%. And just a quick note, I'm just going to tell you these facts rather than kind of prove why they're true. The algebra to show why these hold is a little bit fiddly. I'll post a link to a website that kind of shows these if you're interested. You won't have to do anything like this on a test or an assignment, but just know that these actually come from somewhere algebraic. You can show exactly why these formulas hold. But the mean, or the expected value of this binomial distribution, is just n, the number of trials, times the probability of success. And the variance is n times p times the probability of failure, 1 minus p. Or if you want to view it as instead, mu times 1 minus p. You can view it like that if you like as well. And of course the standard deviation is just the square root of the variance. So in our previous example, we had that the number of trials was 8, we had the probability of success was 0.05, and the probability of failure was, of course, 0.95. So the mean, the average number of people we'd expect to be out on a particular day, is 8 times 0.05. And if we do that, we get 0.4. And you could think, well, you can't have 4/10 of a person, you're right. But remember, this is an average. So this is kind of a long run thing. If we took a sample of a whole bunch of days looking at these 8 people, then the average number that we'd see on vacation is 0.4. And we can calculate the variance similarly. So it's going to be the mean, 0.4, times the probability of failure, 0.95. And we get 0.38. And finally, the standard deviation is just going to be the square root of that. It's going to be 0.6 something. Let me check very quickly. And we get 0.616, so roughly 0.61623 decimal places. So again, this gives you a measure of spread of our distribution, and this is our expected value. Now, in our lecture, we'll actually see kind of the distribution itself. I want to play around with that and show you some graphs, and we'll also do a few problems.